So you could put that in the big snow. That's actually worth a lot. Maybe also the video of like the black bounce of butter. Yeah, it's supposed to be like an art piece. She just had the whip and she just slaps a giant thing of butter. I'll create a video with me. Okay, ready? Do we have a lecture today? We just had a quiz. Usually
I was thinking
I think you didn't answer. Is they really yeah, I got it right now.
they're like,
Well, it depends.
well, I think it's just technology. You're right. I'm still.
That's what I tried to say. I tried out because it's actually broken in EMP and my fries out.
Yeah.
If you want me to redo this one, you can prompt the races.
No, just doing separate sheet.
Oh, separate.
Yeah. Okay, couple of things I want to talk about before we do our lesson for today. The first is I gave back your quizzes, and I made a couple of notes on your quiz. So I said at the top whether I want you to retry certain problems. So those are just items that I feel I want you to make sure you fully understand because it's going to come back. So if I said at the top of the page for you to retry a problem, I just want you to try it on a separate sheet and just show me. I made a note of all the students that I'm going to be asking about those problems. So over the next week, if you get a chance to work through it, just let me know so I can just check you off. I just want to make sure touch base with each of you for those certain problems. For some of you, I may have attached the key so you guys can look at the key for those steps, but you can also look back at your review worksheets for those certain steps. So I made certain notes on your quiz, so look at that and retry the problems. You don't have to turn it into me. I just want to see that you worked it. So put it on a separate sheet, attach it to your quiz so that you can always have something to kind of look back on as you do a further cumulative review. Okay. All right. Any questions about that? Okay. Second is that let me talk about the calendar for a bit. I want to do sketching derivative graphs. I think that is the more pressing lesson for now. This curve sketching graph, sketching a curve graph lesson, we'll get to use a calculator, and I think we can kind of pick out from these problems over the course of the review. So putting it all together, I think you'll get a chance to try these at home when you do your homework. So I'm going to kind of basically skip this because this is kind of like review, putting it all together. And I want to focus more on sketching derivative graphs. Okay, now moving into October, let me talk about the fact that we don't have, we're going to be, having an early weekend, so no school tomorrow. But I'm still going to be following the schedule for the most part. On Monday, I do want to start optimization. Tuesday, Wednesday, we're going to do quiz review. It's going to be a quiz. Initially I had swapped Thursday and Friday. So I'll give you an extra day if you want. So if you're okay with me doing 2 back-to-back lessons before your quiz. So I can move this quiz from Thursday to Monday, but then that means Thursday, I'm going to spend time going over notes for 6.1. Maybe we'll have time at the end to do a little review. And then Friday, I'm going to cover 6.2. Maybe we'll have some more time to review, but that gives you at least additional time to review on your own. I definitely want to get in before PSAT because then it just gets messy after that. So I want to make sure I get that quiz in Monday at the latest. Okay. Are you guys okay with that? All right. So Thursday and Friday, I'll cover 6.1, 6.2. But that also gives me a chance to provide more help sessions. So if you look on the board there, I'm going to start doing help sessions on Thursday. So I'll do Thursday morning, Friday morning, and Monday morning. Okay, help sessions for your quiz starting next Thursday. And then the 6.1, 6.2 homework, this won't be due until Wednesday, until after PSAT day. Any questions with our change in our calendar? All right. All right, let's go to page 37. So what we needed to be able to do is to be able to look at a function graph and to be able to know how to create an F prime graph, an F double prime graph. Another thing we needed to be able to do is looking at an F prime graph and to be able to interpret what does the original graph look like. So kind of going back between function and derivative. And sometimes that can get confusing, especially if you're looking at a graph and you're trying to create a different graph. Sometimes I see students just end up copying the graph that they see in front of them because it's hard to sometimes it's hard to see how they're different. Okay, so let's say we have the original graph in front of us. Okay, I do want to make some distinction here. The reason why this is the original function graph is because the y-axis represents the location of your graph. Okay. All right, so this is a positive y value, this has a y value 0, this is a y value that's negative, y value that's 0, y value that's negative. Okay, so y-axis represents location of the graph, right? We know that. We've been working with a function graph forever. Now, what we're going to do is we're going to create a slope line, and based off of this, and also eventually we'll also do a concavity line. So let's create an F prime sign line, and that's going to kind of give us kind of like a bridge between a derivative graph that we're gonna create on our own. So F prime graph, F prime sign line. We're just going to identify the peaks and valleys, the relative max and relative mins of our graph. So for what x value do you see a relative maximum? Okay, -3. Okay. Where else? 1. Okay, 1. Okay. And where do you see a relative minimum? I know it's a little bit off, but it's close to what? Close to -1. I know it's a little bit off here. Let's just, for purposes of making it easy, let's just say it's at -1. Okay, so let's go ahead and put those critical points onto your derivative graph, derivative sign line. So -3, -1, and 1. Right? These are all the places where there's slope 0 and relative max, relative min occurs. Now, tell me what slopes you see, because everything should be very, very straightforward. What slope do you see to the left of -3? Positive slope. So I'm going to draw an arrow to indicate positive slope. And then it just keeps alternating, right? So negative slope, positive slope, negative slope. All right. Now, these arrows are describing exactly what we see on our graph, right? We see a relative max at -3, relative min at -1, relative max at 1. Sorry, yeah, relative max at 1. All we're doing is, you know, and then the movement of the graphs is exactly what we see with the arrows. Now, we're going to take this and transition it into a derivative graph. So in this middle space here, create a coordinate plane. And we're going to call this the F prime graph. Now, there's a distinct difference now because the y-axis doesn't represent the location of the graph anymore. The y-axis now represents, guess what? It represents the slope value of your original graph. So if the y-axis represents a slope value rather than location, you would expect the graph to look very different. Right? Because slope value is not necessarily going to mean the same as location value. So to help us map out what we're looking at, I'm going to create some labels, and that label will help us decide where the graph is going to go. So that means anything that is living in the positive region, in the positive y value region, these will all represent where my original graph is going to be experiencing a positive slope, right? So anything up here could be slope 2, slope 3, slope 5, slope 6. In general, what's going to happen is we know that everything that's up here is going to end up being where the original graph is going to be experiencing a positive slope. Anything that's below the x-axis on the f prime graph is going to represent where my original graph is going to be experiencing a negative slope. And anything on the x-axis is where my original graph will experience what? A slope 0. Yeah, slope 0. Okay. So we're going to take this and we're going to transition it into an f prime graph. Okay. Now, -3, -1, and 1, these are all places on the original graph where the slope is what? 0. So guess what? These values will go directly on your axis, on your x-axis, because these are all places on the original graph where there's a slope 0. All right, we want to put all the slope zeros on the x-axis. So -3, go ahead and plot that point. -1, go ahead and plot that point. And 1, go ahead and plot that point as well. Okay. These points are very helpful for us because we know these are kind of acting as anchor points. The graph has to go through these points. Okay, it has to go through those points. So that kind of helps remind you. Okay, I can't avoid it. I got to go through. I have to thread through these points over the course of my graph. Okay, next up. To the left of -3, I'm experiencing positive slope. Right? But where does positive slope have to live on my f prime graph? Has to live where? Above the x-axis. So that means this behavior has to be sitting up here, but it has to go through this point. So I'm just going to have a graph kind of go through that point. It seems kind of strange right now because it's like, wait, I have a positive slope, so why does it look like a negative slope? But right now, just think about the fact that I need my derivative graph to be sitting above the x-axis because all these are showing positive slope. So positive slope needs to live here if I'm putting it onto an f prime graph. Right. Okay, between -3 and -1, what am I experiencing? Negative slope. So negative slope has to live down here. So if it's going to live down here, I'm going to have to let this go down into this negative region, but it's has to loop back up because it has to go through this point again. So I'm going to have the graph look like this. Okay. It doesn't matter how far down you go. You just have to just make the smooth curve and eventually have the graph come back up. Okay. Between -1 and 1, what do you see here? Positive slope, so it needs to live above the x-axis. So I have to let it move up into this positive region, but because of that point, it has to come back down. Okay. And then to the right of 1, what do we see? Negative slope, so it needs to live below So I'm just going to have the graph go down like this. Okay. Next up, I want us to go back and highlight some points here. I want us to highlight -2. This, for sake of making it easier, I'm going to call this the point of inflection here. That's where the graph changed from concave down to concave up. And then also at 0, I'm going to call this a point of inflection as well. Okay. We're going to create a concavity sine line. Okay, so we're going to create a second derivative sine line based off of this. Okay, so we have -2 and 0 being our point of inflection. What do you see the concavity being to the left of -2? This is what? Concave down, followed by concave,
Okay.
and then ending up with concave down.
Yeah.
Okay, so over here, we're going to create a second derivative sine line. Okay. Point of inflection. For sake of making it easy with using integer values, we'll say -2 and 0. So go ahead and put -2 and 0. Okay, we said concave down, right? So concave down. These three. Concave down, followed by concave up, and then following by concave down. Now we're going to take this and translate this into an F double prime graph. Okay, F double prime graph. Now, the y-axis is changing again. The y-axis now represents something else. It doesn't represent location. It doesn't represent slope of the original function. It represents what of the original function? Represents what second derivative? Okay. We have different word for acceleration. I know acceleration is an application of second derivative, but what word am I looking for here? Concavity, yeah, concavity. So represents the curvature or the concavity of your original function. So let's go ahead and I want to label what we're looking at here. Anything above in the positive region is going to represent where my original graph is going to look like concave up. It's going to exhibit that shape. Anything above the x-axis represents where my original graph is going to exhibit concave down shape. Anything on the x-axis is where a potential point of inflection is going to live. Okay. Right, so what can I plot onto my x-axis? -2 and 0. Okay, -2 and 0. Okay, to the left of -2, concave down, where do I want this part of the graph to live?
Underneath.
Below, right? Below, but it has to connect to this point, so I'm going to have the graph just rise to that point. Between -2 and 0, above. So it has to go up and come back down. And then to the right of 0, below, yeah. Now, what confuses students a bit is they're looking at this going, wait, it's concave up, so why does it look like it's concave down here? Remember, the concavity is referring to the shape of the original graph, not the shape of the second derivative graph, okay? The second derivative graph, you're just trying to match the location. All this U shape and upside down U shape is meant to show the shape of the original graph, not the shape of graph you're currently working on. Okay. Okay. Now, the majority of the problems that you're going to see is going to be with this, where you're going to be given this graph, and then they're going to be asking information about how the original graph is behaving. Okay, so that's really the main focus that we're going to do. I did it from starting with the function because that's the more straightforward way of kind of connecting everything. But we have to get used to that on the AP exam. Typically, they're not going to give you the function graph, and they could, but typically they're going to show you the derivative graph and ask you a bunch of information about how the original graph is behaving. Okay. Now, another thing I want to point out, this is from a power rule derivative standpoint. Now, this graph here, what degree do you think this graph could potentially be? Yeah. It has a couple of direction changes, right? They're both pointing down, and it's so this could be something in that negative x to the 4 family, okay? Both pointing down, okay? So I want to how to show you that from a calculus perspective, it should match what the graphs that we're creating, okay? So let me ask you this: what is the derivative of negative x to the 4th? Negative 4x cubed. So let me put that here. Y prime is equal to negative 4x cubed. And we see that the graph we see in front of us does resemble the family that we are expecting, right? Y prime equals negative 4x cubed. Okay, let's find the derivative again. What's the derivative of negative 4x cubed?
Negative 12x.
Negative 12x squared. Y double prime is equal to negative 12x squared. We can convince ourselves that this is matching with what we expect from a derivative standpoint. So it's nice to see a derivative connection with these graphs that we're creating. Okay, two more things that I want to point out is that if you're looking at the derivative graph, the peaks and valleys of your derivative graph is going to match up nicely with the point of inflection of your original graph. Okay, so the peaks and valleys of your derivative graph is where the points of inflection is going to be. The reason why, let me kind of talk about a little bit about that reason, is that the point of inflection typically is going to be where the steepest slope is going to be, right? Either the maximum slope or the minimum slope. So that's why it shows up as the peaks and valleys of the f prime graph, because the higher it goes, it's going to indicate the maximum positive steepness. And here, this will indicate the minimum steepness, and that's going to translate to these point of inflection. Another thing that kind of throws students off is they're looking at this and saying, wait, if it's a positive slope, then why is this showing me why does this looks like it's decreasing? Okay, why is it decreasing? The reason why it's decreasing is because these are all positive slopes, but these are all different variations of positive slopes. All right. So I just want to highlight a couple of these. I'm just going to ballpark some of these slope values, right? So maybe this is a slope of 4, then 3, then 2, then 1, then 0, then -1, -2, -3. So imagine plotting all those slope values onto a graph. This is what it's going to look like: 4, 3, 2, 1, 0, -1, -2, -3. Okay. Another thing I want to point out is that whenever your slope is decreasing like this, right? You see how all these slope values are moving in negative direction? That's indicating to me that my concavity is what? Concave down. So a concave down on the original graph is going to look like a negative slope on the derivative graph. So wherever the derivative graph is showing a negative slope, that's indicating to us that the slope is decreasing, and the slope is decreasing, that's going to look like this, and that's going to translate to concave down. So if you look over here, from -infinity to -1, it's all showing, sorry, to -2, it's all showing concave down. The positive slope of your f prime graph is going to translate to concave up on the original graph. A negative slope on the f prime graph is going to translate to concave down on the original graph. Right. Okay, all right, let's go to page 38. Okay, so this is mainly what I want to focus on. Can we look at an F prime graph, create slope and concavity sine line, and then sketch what the original graph and what the second derivative graph could look like? All right, so this is the F prime graph. So if this is F prime graph, let's remind ourselves the y-axis represents slope. Of f of x. So to help remind us of this, this is not the original graph. So I can't say, oh, there's my relative max, there's my relative min, there's my relative max, right? This is not the f of x, this is f prime. So I like to always label and map out what I'm looking at. So anything above is where my original graph is going to be experiencing positive slope. Anything below the x-axis is where my original graph is going to be experiencing negative slope. On the x-axis is where my original graph is going to be experiencing a slope 0. So let's create a slope sine line. And then I like to use a slope sine line to kind of act as a bridge to whether I want to go from f prime to f or from f to f prime. Okay. So here's my sine line. Okay. I'm going to put all the slope zeros onto my derivative sine line. So not slope 0 in terms of the slope, but slope zeros in terms of location here. So what can I put onto my f prime graph? Okay. -4, -2, and 1, right? These are all the slope zeros of the original graph. So -4, -2, and 1. Okay. Now, to the left of -4, what do you see? Yes, right. Don't look at the slope. That's something else, right? Look at the location. It's clearly sitting below the x-axis, and that's going to translate to a negative slope on the original graph. Between -4 and -2, where is this located?
Above.
Above, yeah. Don't look at the shape. Look at where it's located, above. So that's going to translate to a positive slope on my original graph. This third region here, below. And then the last region, also below, right? Also below. Now, we're going to create a graph that's going to resemble the movement of these arrows. Okay. And what I'm going to do is I'm going to cover this graph, because if we are looking at this graph and trying to do f of x graph, you're going to potentially end up just copying what you see. So I'm going to purposely cover this up and just force ourselves to just graph based off of these arrows. Okay, so let's say you're just trying to make a graph based off of these arrows, and that's what you want your graph to look like. You want your graph to, what do you expect here at -4? A what? A relative
Minimum.
min? What do you expect at -2?
Relative max.
And then at 1, neither, right? It's going to flatten out, but it's going to continue going down. Now, it doesn't matter where that relative min is. It doesn't matter where the relative max is. As long as you have the shape, that's all I care about. So I'm going to pick points that are obvious in terms of, okay, I'm going to purposely pick a low point on the curve for relative min. I'm going to purposely pick a high point, but you don't have to do that. As long as your shape looks like my shape, doesn't matter where the location of your graph is. So at -4, I'm going to target a low y value because I want my graph to go down to a relative min. At -2, I'm going to target a high y value. And at 1, it doesn't really matter. I'm just going to maybe pick a point somewhere between. Okay, so now I'm going to follow the arrows. What the arrows are telling me, I want my arrows to decrease. So decreasing. It's my relative min at -4, rises to my relative max at -2. Reaches my relative max, decrease to some point at 1, flattens out for a moment, and then continues to go down. Now look, it should look nothing like your f prime graph. Okay, if it does, that means you may be copying it without following your arrows. Next up, let's create an f double prime graph based off of your f prime. Okay. So we're going to find the places where the maximum steepness is going to occur. And that is going to be where your points of inflection is going to live. So the peaks and valleys of your F prime graph is where your point of inflection is going to live. Okay, so what are those X values?
-3.
-3, -1, and 1. Now, concavity is based off of whether the slope is become more positive or negative. Don't look at the curvature, right? This is not the curvature of the original graph. So just look at the slope, right? Wherever there's a positive slope, it's indicating where the slope is becoming more positive, and that's going to translate to a concave up. So in this region, we can say that the original graph is going to look like what? Concave up because it's positive slope. Anywhere there's a negative slope, that is indicating that my original graph is going to show concave down. Positive slope, concave up. And negative slope, concave down. And we can kind of see that within the graph that we created, right? Concave up to begin with, then it shifts to concave down, then it shifts to concave up, and then it shifts to concave down. Right, so the concavity will kind of match with the shape of your original graph. Okay, let's create a second derivative graph. Okay. Again, I like to label so that I'm putting everything in this right place. Above is concave up, below is concave down. On the x-axis is your point of inflection. Okay. What can I place onto my x-axis? -3, -1, and all right, so don't look at the curvature, look at the location. Where do I want to the left of -3 to live? Above. So it has to go down and connect to this point, right? These are my anchor points here. Between -3 and -1, below. So go down and loop back up because those points are guiding my next steps. Between -1 and 1, above. And then to the right of 1, below. Now, this is the easy part. Writing out all your increase, decrease, relative max, relative min, concave up, concave down. You just read it off of your sign lines. Whatever your sign lines are telling you, you can just copy all those characteristics down. So I like these. I like having these sign lines. These sign lines helps us fill out characteristics. These sign lines also help us act as a bridge to the graph that we want to create. Okay. After we do this, then I want us to finish with number 4, and then we'll be done. Okay. I'm just really pulling the data directly from my sign lines. Okay, let's try number 4. Go ahead and try number 4. I'll work the problem the same time that you do, and let's just see if our steps matches up. Okay.
G of X and FX the same function.
Sorry, yeah, I meant for it to be all G. So everything is G prime, G of X, G double prime. Sorry. As you create your G of X graph, cover up your G prime. If you start looking at your G prime graph, you're going to start copying it. The only thing you want to look at is your sign line. Your sign line is going to tell you exactly how your graph is going to move. Again, it doesn't matter where your Y values are. As long as your graph matches the movement of these arrows, that's all we need. That's all we need to know how to do. A good way to check is your G of X graph should look nothing like your G prime. Okay, if they look exactly alike, that's a red flag. Something is not quite right. The slopes of your derivative graph is going to tell you what the concavity of your original graph. Negative slope on the derivative graph translates to a concave down on the original graph. Positive slope on the derivative graph is going to translate to a concave up on the original graph. Okay, good. I'm glad that we were able to get through this. We only have optimization to do. And optimization, we're just going to be looking at a few cases of optimization. So that shouldn't be a big deal. Check your calendar for your homework. So Thursday and Friday's homework, you guys have a long weekend to finish that. I'll send you guys the updated calendar or schedule for the next week on Sunday, and then give you some reminders about our upcoming help sessions next week. All right, come get your phones.
Here's the question. Yeah. So on this one, you already answered for the last question. You say the right answer. This one, it's like
So we also need to find the derivative of this left side. So the derivative of that log y is 1 over u times u prime. 1 over log. And you have all this whole product roll on the right. So I gotta bring that y up, right? Because y is equal to y prime. And that's the line. Yeah. And then this is a original function to begin with, so I can replace the y back with my original.
I see. Okay, thank you.
Okay, that's great. Yeah, any questions? Okay, I'll mark it. Thank you.
So for this, why would this arrow be?
Too far up at the side.
Oh, you mean at -2?
Yeah, and like.
Now I know.
Yeah, this is positive.
Now I know.
Oh, positive though, flattens out and positive. Oh, yeah, we always read the graph from that way, even though the arrow's pointing this way, we should read the graph.
Okay.
Honestly, W.
Have a good weekend.
There was a class. Their class average, their class average is like 1.